All right, so last class we talked about context-free grammars, what they're useful for, what their limitations are. And if you look at our journey, we started with, circuits. They had their limitations, but they were great because there are physical devices that you can build out of them, and which are the basis of many modern computing architectures anyway. Then we generalized them to DFAs, which had their own limitations. Then we went to our all-purpose computer, which was the Turing machines, right? That we kind of studied them in depth. And what we're going to do today is study a new model of computation. And this course, as I kept saying, is about understanding models of computation, right? What are your devices? We want to build models which are time resilient, and we kind of achieved our goal so far, except they're not physics resilient, in the way that we usually think of things. So let's try and do that in the next 3 lectures. Do you hear a lot of echo, or is it just me? Let's see. Okay. And, I posted this poll on EdSTEM, and it seems like quantum computing was the most favorite topic by far. So I'll honor your wishes, and let's talk about quantum computing. Okay, so this is the first time I'm teaching it, so bear with me a little bit. Give me ask me lots of questions, give me more feedback as we go along. Okay, so we have 3 lectures. My goal is to first talk about quantum weirdness. There's a lot of weirdness in the world, but quantum weirdness is at a totally different level. And then we'll talk about the basic model of a quantum circuit, right? And that's everything. That's a complete model of quantum computing, of a quantum computer. And it's something that we have all the tools needed to talk about, given everything that we built. And then we'll see one application, okay? There are many, many stunning applications. Obviously, we cannot cover all of them, or nearly a reasonable portion of them, but we'll cover one application, all right? And just as an announcement, homework 5 is already up on the website. So the goal, as I said, we need to first understand what is a qubit, how do we compute on it? That's our goal today. We're going to talk about a single qubit, like something that operates on a single bit, more or less. And then we'll talk about quantum circuit in the next class. In the 3rd lecture, we'll look at one stunning application of quantum circuit. Okay. All right. First, quantum weirdness, right? I mean, you might have seen this in popular culture and popular science books and so on. But every time I think about it, it is still weird. Anyone says they understand quantum mechanics, either has spent 10 years studying it, or is just not speaking the truth, to put it politely. Okay, so let's consider a very simple experiment. Okay, this is something you and me can, if you give me enough time and a little bit of budget for setting it up, we can do. Okay, it's not something crazy experiment where you need some ultra precision equipment to do. So I have a baseball gun which shoots out baseballs like I do at random directions, but with enough velocity against a wall, and there is a
just imagine we're in our CS lecture together.
I don't know about it.
behind. This is a brick wall, so the balls can only go through the hole. But when they hit the wall, they leave a dent, the plastic wall, right? If I shoot it like this in random directions, what do you expect will happen? Any guesses? How would the wall get dented? Yeah? Right. And somehow you can, you would see more of a dent like this, right? Okay, it would kind of distort more when it's aligned, let's say. Okay, you can imagine the baseball machine is sufficiently far, the off angles, maybe 1 or 2 get through, but not that many. Okay, kind of in the middle, you'll see a dent like this. Okay, very simple experiment.
Professor, we can't hear you.
Can you hear me now?
Yes.
Oh, okay, great. All right, let's get back. Okay, so you'll get like a two-dent distribution, right? Makes perfect logical common sense. Okay, something like this, right? The wall would be bent to look something like this, and you have these two big holes, so that's where most of the balls would hit. Others might see some hits, but this would be the distribution that you get. Oh, okay, sorry. Can I share a screen? Okay. Who is the host now? Somebody, whoever is the host, can you make me a co-host? I don't know who's the host. Does anyone know who is the host? Oh, I guess. Can you make me the host? I see. So basically, if I get disconnected, the person who joins first becomes the host. It's a good protocol. I can live with that. Thank you, Shimeng. All right. Okay, we are back. I think we have audio, we have screen sharing. Okay, so we'll have this double slit, this bimodal thing. Because everything so far is very classical and nice. Such a nice world we live in. Okay, but then comes the weirdness. Now, suppose I did something similar, but okay, so I do the same thing, but now instead of a baseball gun, I have a laser gun. Okay, that shoots photons. All right. And let's say this is some kind of light sensitive surface. Okay. So now if I do single slit, okay, let's first talk about the single slit. Well, what happens is basically you'll see a bright patch here just like, we were seeing with a single baseball, right? There will be some kind of brightness here and kind of deteriorates slowly. Yes, some light goes through, it's shooting photons, individual photons, and you see this. Great. This seems natural enough. And although you can also ask what happens if I do the same thing with double slit. Okay, now I put two holes, but I'm shooting photons again. Again, light sensitive surface. Guess what happens? No one can guess. If you're guessing, then you've seen the answer. So what you get is one of the weirdest things ever, which is you don't see this bimodal kind of thing. What you see is something like this. Okay, so when you create the extra slit, you would think, among many other things, that whatever is going through earlier can only get brighter, right? But somehow opening the second slit makes things which were bright in the first slit was open, kind of become completely dark as well. Okay, so you see this quote unquote interference pattern. All right, and this happens even when you make the laser gun precise enough that it's shooting exactly one photon at a time. Okay, you're shooting exactly one photon at a time. You see the same thing happening. If I put a detector at the slit, then this phenomenon goes away. Okay, if something tells me, okay, did a photon pass through, it goes away. So when both of the slits are open and there's nothing in between, you see this destructive kind of interference. I mean, it is what it is, right? We don't know why it's happening, at least currently, but there's something that only quantum mechanics can explain. That's quantum weirdness number one. And one way to explain this is like you have probabilities that can cancel. So we'll see, what this precisely means in a little bit. So we'll have probability with negative numbers and so on. Okay. So tons of experiments and devices where the usual rules do not explain them. Okay, this is one of the most famous one, and that's where we started out with it. Okay, and why is this important for us? It kind of started out with a goal that people wanted to do, right? Which is, how can we simulate such a system? Okay, if you have all this quantum mechanics stuff, how can I simulate such a system? And we definitely know that nature is quantum. There is no going around it. And as a result, there is no obvious way, obvious algorithm to simulate a large system on a computer. You can simulate large quantum system on a computer efficiently. Okay, so you can do it, but with some exponential losses, it's not very efficient. Okay, so this people knew for a long time, but then came this sort of almost tautological insight due to Feynman, among others, who said, if nature gives you lemons, what do? Well, you make lemonade. Right? No sugar coating it.
Oh.
Okay. So in some sense, if you cannot simulate the system on your traditional computers, then what can you say about the system? It is a computer which is doing something powerful that your system is not able to. Okay. As I said, it's kind of a tautological thing, right? You're saying if you cannot simulate a system efficiently, then the system can be seen as performing powerful computations by itself. Whatever the system is, this is something that we see in nature. I can set up something and see what happens. So I can do this experiment. Okay. So the idea at a very, very high level is the following. So you set up the initial state of a quantum system, meaning it obeys laws of quantum mechanics, right? All those destructive interference patterns and whatever you have, we evolved using quantum mechanics, right? And then you get one. So you want this to be useful for something. Okay. So I have some problem, computational problem that I want to solve. Mainly, I can set up the initial configuration of some quantum system in such a way that if I then apply, let it, do its own quantum magic, just let it do its own quantum mechanics thing, what I get out is something useful for me, right? This is the rough idea of what quantum mechanics is. So somehow what you'll do is you have your photons, and then you'll put all kinds of obstacle courses in between. Think of them as like all these gates, as we will talk about. These are all performing quantum mechanical operations, okay? So you need to use laws of quantum mechanics to figure out what they're doing, but we're not going to figure out. We're going to let it do its own thing. And the answer will tell us, whatever the output is going to be what we want. Okay. So you're going to set up the photon through some obstacle course, and they will magically solve the computational problem that you want. All right. And that's the, view or bird's eye view or satellite eye view. Okay. And this was made much more formal by David Deutsch in 1985, who formally defined quantum Turing machines. Okay, and it's no surprise that when you wanted to define quantum mechanics, quantum computer, the right thing to generalize is quantum Turing machines. Okay, and this was subsequently developed much further by Josa and Bernstein and Vazirani to what we call essentially quantum computer. Okay, so we're not going to define quantum Turing machines because it's a bit too. We had to, just as we did for classical things, we started with circuits and did many other things before we defined Turing machines, right? So, kind of, following the same template, we'll stop with defining quantum circuits. Okay, and that will already, show us the power and abilities that quantum mechanics has for computing purposes. Okay. That's the high level picture, and we'll talk about more of those kind of bigger computational questions later on. But today we had to talk about what is the most basic object in quantum computing, which is what is a qubit. You might have heard this name qubit in many places. I should say that there's a lot of misinformed hype around quantum mechanics. I hate whenever I see that. So hopefully, if not anything, anytime some investor or some startup person comes and says, I have a quantum computer which explores all things exponentially in parallel, you can just shoot them in the foot. Okay. All right. So before we talk about what a qubit is, let's talk about what is a bit. Well, what is a bit? What is a bit? Mathematically, it's just something which takes 0 or 1, right? But it's kind of nice for us because you also have physical representations of bits, right? If you have a semiconductor, then somehow low voltage corresponds to something like 0, high voltage corresponds to something like 1. Okay. So essentially, you have a system which is in one of two states, and you're calling one state 0 and the other state 1, and that gives you a physical representation of a bit. Okay, that's all the main thing of a bit is, right? Now we have something similar in the quantum world. So you'll have electrons, and they have something called spin. Don't ask me what it is. Okay, so we're going to work at these things at a pretty abstract level in formulating the laws without specifying how they correspond to devices. Okay, that's a whole different kind of area and much more active than what you think of is for classical circuits. Like for circuits, we can implement, we can design, we can manufacture all of those things, right? But quantum circuits are in a different stage. But first we need to know what they are. So spin, it has something like two states again, something called up, something called down. You can think of up as being 0, maybe down as being 1. Okay. And similarly, you also have photons. In fact, we'll use photons throughout because there's actually something you can get your hands easily on and see some of the things if you want to as a holiday project. I might do it with my daughter who is 5 years old, but. Okay, so they have two states just called polarization. Like, you have polarized glasses, right? When you put them on, when things get dimmer, right? And essentially, they're all polarized glasses are basically horizontal polarizers. So they have two kinds of polarization. So each photon you can think of, again, as either having some horizontal polarization or vertical polarization. And if you're a classical person who doesn't know quantum mechanics, you would say, okay, the horizontal polarizer only lets in photons which have horizontal polarization on them. Okay, but that's not as we will see. But that's kind of what happens. That's why light drops out 50% and so on. Okay, so far so good. Nothing non-trivial has happened. We're still in a world where everything is binary, but now here comes comes a world which is not binary. Okay, so the first law of quantum mechanics, we will generalize it later on to higher dimensional things, but let's just focus on a single qubit. Is if a system can be in one of two options, okay, we will denote the two options as this 0 with this strange notation. It's like a slash and a greater than symbol. Okay, this is called a ket. I will talk about the notation later on. It's very, very helpful for making many of the calculations easier. Okay, there's no reason to do it besides making our calculations and notations much nicer and clearer. Okay, so there's no other magic thing. So this is just Like a bit 0, we were denoting as 0 earlier, bit 1 was 1. Now you have two states. One I'm going to denote with a 0 in the strange ket notation. This is called a ket. And 1. All right. Then it can also be in a superposition of the two. Okay, so there are two options. The actual system doesn't necessarily have to be in just the 0 or just the 1 state. Okay, it can actually be in a superposition of the two, meaning something like this.
I think it's because the mics get too close to each other. I don't know.
Some interference, some quantum effect. Okay, so we have the superposition of the two, which is given by some combination of the two states, but it's not a traditional combination. So you have alpha times 0 plus beta times 1. So it's basically two numbers, right? And we'll denote as this alpha 0 plus beta 1. Again, this is all notational at this point. But the main thing is you have two numbers, alpha and beta, which describe the state of the system, right? Where alpha comma beta are two numbers with alpha squared plus beta squared equals. Okay. So if you take a quantum mechanics course before, then you would have seen that these are complex numbers traditionally, but we don't need complex numbers. All you need is real numbers. That's enough to do all of the magic of quantum computing. So let's just stick to them as two real numbers. Okay. But having complex numbers, again, when you go beyond just the 3 lectures that we're going to do, makes many things much nicer and much clearer. Okay. And yeah, two real numbers, but the main thing is that they can be negative. Okay, they can be negative, positive, anything that you want, right? So for example, so let me put this in the box. So the system is described by two numbers now, alpha and beta, which are whose squares add up to 1. Okay. So for example, you might have 0.8 times 0 plus 0.6 times 1. Okay, that's 1. Why? You can check, 0.8 squared plus 0.6 squared is 0.64 plus 0.36, which is 1. Okay, so this is a valid qubit. So qubit is now just described by these numbers alpha and beta. Every possible alpha and beta corresponds to a qubit. And you can also have, so the qubit can be in many of these states. Like these two are genuinely different. Okay, and you can see the difference physically under some devices, right? You can also have something like just 0. This is also valid. Yeah.
So the addition of these two constructions is one qubit.
Is one qubit. So one qubit basically has two things, two options, and is described by this alpha and beta. Okay, the pair alpha and beta describes one qubit. Okay. And you can also have, one, it's really like 0 times 0 plus 1 times 1, but we kind of skip this 0. Oh, sorry, this is 1 times 0 plus 0 times 1. We just kind of shorten it and write it just as 0. Okay. And yeah, same thing here. You can also have something like okay. This particular state is important enough that it gets its own name, which is plus. Okay. And you can also have 1 over square root 2 times 0 minus 1 over square root 2 times 1. Again, this is good enough. I mean, appears often enough that we give it its own name, just minus. Okay, so all notation for now. Plus means you have 1 over square root 2 and 1 over square root 2. Minus means you have 1 over square root 2 and minus 1 over square root 2. All right?
Basically, they're even. The magnitude is the same.
Right. And you can picture the state alpha and beta as a point on the unit circle. Okay, so like this is alpha comma beta, because we know that alpha squared plus beta squared is 1, right? So the state corresponds to a point on this circle, right? So state corresponds to point on circle. So if you were to visualize it, you can say that this is 0. Okay, and this is 1. What would this be at 45 degrees angle? Which is plus, right? And minus would be this guy. Maybe I should use different colors. Okay. Any questions about this? I mean, we didn't do anything so far. We just kind of defined some notation to say we're going to talk about vectors in this weird ket notation. And we call these qubits. But what do you do with it? That's what determines what really happens. Okay, let me see if I can fix this without wasting too much time. Or change the pockets. Okay. This seems to be doing better. All right. Okay, I mean, that's fine. We formally define what a qubit is, but the question is, what do you do with a qubit, right? So what do you do with a qubit? And the answer to that is really what distinguishes quantum mechanics from the usual laws of physics, Newtonian laws of physics, and the quantum computer. Okay. So what you do with qubits is you can measure them, right? So now, if I tell you there's this box, the photon is in this alpha and beta state, I want to know what is alpha and what is beta. Can you know that? You cannot really know that, okay? But you can probe it to get some information about what those alphas and betas are, right? So you can have these devices, it's called measurement devices, okay? And let's take this analog of this photon, which has horizontal polarization, which we denoted as 0, vertical polarization, which we'll denote as 1, okay? So 0 is horizontal polarization, 1 is vertical polarization. Okay. Now you have these devices or measuring devices, which are denoted something like this. And let's call them this. And suppose I put a tiny hole here and here. If I send a photon in, okay, the state of a photon is usually denoted with this Greek letter psi. And that's just some alpha times 0 plus beta times 1. Right? We said the state is just these two vectors. And now when I pass it through this measuring device, what happens? And that's what really changes when we talk about quantum mechanics. Okay. And here's where quantum mechanics law 2 comes in. So law 1 was, it can be in a superposition of these two states. Law 2 says when I pass it through this device, especially for the photon's sake, and we can generalize it to many other devices later on, what happens is you'll see an outcome. So this measurement meter is going to say, okay, you are in horizontal polarization or in vertical polarization. Think of it as a digital readout. It says, okay, H or V, right? But it's not a deterministic reader. Okay, that's just the way nature works. You know, you don't ask me why, right? Don't ask me to explain why. Okay, that's a law of nature. So when I pass it through this, what you'll see is it reads, you know, it says horizontal with probability alpha squared, okay? And it will say vertical with probability. Okay. When I pass it through this measurement device, it reads out horizontal. Okay, the photon was in horizontal polarization with probability alpha squared. It was in vertical polarization with probability beta squared. Okay, you should not say it reads out the photon was in this, because that doesn't make sense. You should just say that when the photon interacts with this device, it will say H with probability alpha squared and V with probability beta squared. Okay, this is the most basic piece in a quantum computer, and everything in quantum mechanics. Yeah.
A squared plus B squared. Why wouldn't we just define it as A plus B equals 1?
Because they can be negative numbers, right? That's important, right? As we said, these can be negative numbers. Okay, so if they were positive, then if you only put positive numbers, everything would just be classical. It's just like probabilistic computing, in fact. So you wouldn't get any advantage over traditional computer. Okay, the point is you can have negative numbers, and as we'll see, we can exploit it very critically. Yeah.
So this is the equivalent to saying this is a 1 with this probability, this is a 0 with this probability.
At this level. Okay. But the fact that this alpha and beta are negative, it kind of hasn't showed up so far, right? It's not something we have used, right? As was asked, like, what if I just put alpha squared as A and beta squared as B? I said that was the state. Nothing has been changing, but we'll see something strange happens when you have this negative things. Okay. And so let me say it. So the measurement device says H with probability alpha squared, V with probability beta squared. Okay. So usually when you think of this measurement, you can say, okay, you measured it and the photon got absorbed at this time. Okay. But in nature allows you to say something more. What does nature actually do? When I pass it through this measurement device, it doesn't just read H and V. Okay, it also changes the state of the photon that goes in. Okay, so the photon, it doesn't get absorbed. You can assume it gets absorbed, but actually you can build devices which do not absorb it, kind of transform it. That's what we're going to do. So what comes out is actually going to be just the 0 state with probability alpha squared and 1 with probability beta squared. Okay, so if I pass something in this sort of superposition state through this measurement device, I'll get something which is not in superposition. So just the 0 or just the 1, where each one happens with some probability. Yeah.
Is this equivalent to like more general quantum mechanics when you observe something and it collapses from a
Exactly, it's the same thing, right? Right. But we are specializing everything just to 2 options. In fact, if you think of quantum mechanics, when they talk about protons and so on, photons and so on, it's not just two, right? It's a position is on the real line and many things like in this whole continuous thing, we're focusing on like two things. It's kind of strange that they don't do this first, but they do the real line, waveforms and so on, just gets so much more complicated. Whereas if you do it this way, you can already see the amazing sort of non-intuitive things happening in a much simpler setup. Okay. So as was asked, this is important, which is measuring changes the state. Okay. And no way to know alpha, gamma, beta without changing them. Okay, there is no way to probe and see what this alpha and beta values were without actually sending it through some kind of measurement device and then seeing that it changed the state, right? So this is kind of another example of quantum weirdness. Or you might have heard of the uncertainty principle. Right, if a car is moving at a speed 60 miles per hour, I can see that it's going at that speed without changing the speed of the car, right? But you cannot do it at a microscopic level, and that's one of the fundamental tenets of quantum mechanics. Okay, and the way it manifests is exactly this. I do this measurement, and what comes out is something like this. Okay, sounds very silly, right? You know, not very powerful. Okay, it happens with probability alpha squared, happens with probability beta squared. So what? But as we'll see, we can just use this point to build many amazing things. Yeah, any question?
Yeah, if you pass in like a photon that's already in state 0, then there would be no mutation, right?
There will be no mutation, exactly. It's already one, so you just go with, in fact, yeah, let's do some examples. I think that's a good thing to just try and understand this simple thing. Okay, so let's do some examples. Okay, so as just was asked, suppose I send in something which is just no superposition 1 times 0 plus 0 times 1. Well, alpha squared is 1 and beta squared is 0, right? So you just get 0, and this happens with probability. Let's say I do maybe 0.80 plus 0.61. Then I'll get 0 with probability, kind of, roughly 2/3. Okay? And 1 with probability 0.36. If I do 1/√2 plus 1/√2 times 1, which is a plus, then you get something like a uniformly random, like, intuitively uniformly random bit. So what you get out is in state 0 with probability half and state 1 with probability half. It's like, tossing a coin. Okay, yeah.
Why do you distinguish between plus and minus if the detector can't?
This detector can't,
Yeah, okay.
right? But other detectors can. Okay, and that's going to be the quantum mechanics law number 3. Just these two are not enough. You need one more law, and then we are in position to do everything in quantum computing. Okay, but we just had to put these things together. Any questions about these things so far? All right. So, we kind of defined what's the state of a qubit, and we looked at an example of what a measuring device does, right? You have this horizontal filter, polarizing filter, and so on. Okay. The good thing with, okay, so we'll get to that in a second, but you can actually illustrate Well, okay, maybe first I'll define this and then I'll tell you the non-trivial thing. So the third law tells you what kind of measuring devices you can build. Okay, if the only thing that you could do was check whether it was a horizontal or vertical polarization, that itself would not be useful. Okay, I mean, it can be useful with other things, but there are different parts of this third law, but I will state the most general one, and then we'll specialize to the most useful one for us. Okay. So let's say 3A is we can build a device that rotates the state by an angle. Measurement is destructive. Okay, if I measured it using this horizontal or vertical, the original state kind of destroyed, and I got either a 0 with alpha square probability or 1 with probability beta square. Okay, but I just see the single outcome. I don't know, I don't get to do it again and again and see what those alphas and betas are, right? But you can also do some non-destructive operations. Okay, so let's say this is your state. Then I can build a device. I think of this as like the photon going in, and this is a rotation device. Physics allows you the ability to build these devices. Okay. In fact, if you go to a dollar store, you get the ability to do this, get a polarizing lens, rotate it by theta, then it becomes a rotator. Okay. Sometimes nature is kind. Okay, so you get something which is the same state rotated by theta. And this was the old one. The new one would be like angle theta more. All right. So for instance, if I pass in the state 0, what would I get out of it? Well, you can see, right? Let's say I'm in, this is 0. If I rotate by theta, I should move here. Now, what is this point on the circle? Well, but we also know the exact formula with trigonometry, right? So it's cos theta comma sine theta, right? So, okay, so the projection along the x-axis is like cos theta, right? And the projection on the y-axis is sine theta. Okay, so what you get out is cos theta times 0 plus sine theta times 1. Okay, if I pass in 1, I get, again, you can compute it. You get this vector, right? It's transforming the state. So you get minus sine theta times 0 plus cos theta times 1. Okay. Why does nature allow us to do it? It allows us to do it. Let's just use it. It gave us lemons. Let's make lemonade. Okay. Any questions about this? So nature kindly doesn't just allow us to rotate, but also allows us to reflect. Not on our own existence, but around a line. Take any line through the origin of the circle.
Look up the U and about.
Hmm?
Look up the U and about.
Okay, thank you. Do
Number A instead of
oh yeah, thank you. Okay. All right, so you have take any line like this. Maybe I'll choose a special line in a bit. So this is like the standard X and Y axis. And you can build a device. If I pass something in state, here, what comes out of this device? Reflection is going to be so what comes out is the reflection of the black point around the cyan line, right? So you'll get something like maybe here. Okay. Again, this is a physical device which we can actually build this device. When we talked about circuits, we said, okay, there is something which takes the 2 bits and outputs the AND. Here, give me any line, I can build a device which transforms it this way. All right. Now, so for example, there's a very special line and a reflection around it, which is the line at angle. Okay, let me draw it carefully. So we have 0, we have 1, and the line that we're going to focus on is the one at 22.5. Okay, 1/4 of the quadrant. The reflection around this line is a very important operation. So reflection around the line with angle 22.5 degrees. It's called the Hadamard gate. Okay. So what does this do, right? Let's kind of get a sense of what this gate does. Okay. If I pass in 0 through this Hadamard gate, what would you get? Well, we can compute it, right? Exactly, right? You can, kind of, it's nice that you have all this very complicated things that you're going to do, but you start out with like, middle school geometry or something, right? So you just reflect around this line and you get, so you're reflecting 0 around the 22.5 degrees. So you go 22.5 degrees out the other side. So you end up with 45 degrees, which is 1/√2, 1/√2. Okay, so you get the point 1/√2 times 0 plus 1/√2 times 1. Okay, and we'll talk about this Hadamard gate mathematically in the next class, like, what is the way to represent it? It's really a linear transformation, so it corresponds to a matrix and so on. But, we don't need that for the time being. And if I pass in 1, what do you get? Okay, so if I reflect minus I get back this point, which is, sorry, if I reflect 1, I get back 1 over square root 2 minus 1 over square root 2. Right, exactly. So you get minus. Okay. So now we have the most important pieces in defining quantum circuit. The fact that we can rotate things, and we also know the 2 laws. Okay. The third law, I only described it partially, like, there's 3a and 3b, which tells you can build a device that rotates some by angle theta. You can reflect around origin, and combining this 3a and 3b and 2, right? So imagine I rotate and then measure. I rotate and then measure. I rotate and then measure. I can do these things in various combinations. And that's what a quantum computer is. Rotate, compute, rotate, rotate, compute, rotate. Okay, that's kind of the slogan in which you can understand quantum computers. Okay, but before we go there, let me actually state the law that we really need. Okay, so for what kind of device, measuring devices can we build, right? A corollary of 3a, 3b is that for any 2 perpendicular vectors, u, v on the unit circle, what can you do? You can build a device which basically does what the horizontal polarization filter was, horizontal measuring device was doing for these 2 vectors. Okay, so meaning I can build a device, which again will denote something like this. So UV, so let's say UV device, such that if I pass a photon through it, then what you get out will be in the state U with probability something and V with probability something. Okay, so best way to think of this something is geometrically, right? So when we had the point on the circle, right, this was alpha and beta, and we had the 0 and 1 basis. Okay, when we passed it through the measuring device, we said we are going to get 0 with probability alpha squared. What's the geometric meaning of alpha squared? Any guesses? How can you infer alpha squared from this picture? It's the length of the projection of the point alpha beta along the x-axis, right? If I project along here, this is exactly alpha squared, right? And if I project along here, the length is exactly beta squared, right? When I write it in Cartesian coordinates, when I write it as x comma y, x is the projection along the x-axis, y is the length of the projection on the y-axis. Okay, so instead of saying, okay, when it's alpha and beta, you see 0 is probability alpha squared, I could have said you could see 0 with probability proportional to the length squared of the projection of the point. Okay, and the advantage is that this is kind of invariant to picking other bases. Okay, I'll write it down and then we'll explain it. Probability length of projection onto So you would get, so if I have general basis, two perpendicular vectors, I build a device, I pass it through it, then this is what happens. Okay, let's take a 5-minute break. And when we come back, we'll do some examples of this quantum mechanics law 3. And we'll do, 2 simple examples to illustrate the non-trivial things that we can already do with these basic things. Okay, in the next class, we'll see how we can put this together to get our quantum computer. Okay, all right, let's take a 5-minute break.
Recording in progress.
So let me emphasize something about quantum mechanics law number 2, right? The important thing to keep in mind here is that you don't see the probability. The outcome is either in state 0 or in state 1. Each of them happens with some probability, but you kind of only see one realization of this toss. Okay. So if I just do it once, there's no way to know what was there happening before. This event happens with some probability, but only one of these two comes out. And why it collapses? That's kind of one of the deep mysteries of quantum mechanics. You can justify it by using all kinds of other experiments and things, but this we know for sure is the foundation of quantum mechanics right now. Okay. And there's this famous sort of saying attributed to many people, also to Feynman among others, like everything in physics is, but the quote is kind of crass, but I think captures many things. If you want to try to start asking questions like, okay, why is this collapsing? What is the interpretation? What is the meaning of these numbers and so on? People were fighting over it for a long time. And then someone said, look, just calculate, everything works out, every experiment checks out. So just calculate and you'll see the answer. Okay. And to do these calculations, you need familiarity with computing lengths of projections. Okay, it's not as bad as saying that if you want to learn opera, you need to learn Italian, but you just need to know how to compute projections of lengths of projections of vectors. Okay, so let me summarize. So law 1 is we have superpositions. So state corresponds to alpha and beta. These are 2 real numbers. Okay. You can think of them as, as a vector in 2 dimensions. You can think of them as alpha times 0 plus beta times 1. Okay, both are equivalent, whatever makes it convenient for you, right? Quantum mechanics law 2, when we measure in H and V, we see 0 with probability alpha squared, state becomes okay. And there was also law 3A, 3B can rotate state, can reflect state. Okay, there's a general form of this, which is that you can do any linear transformation that preserves the length. Okay, when you rotate, you're still being on the unit circle. And that is important because the probabilities should add up to 1. Okay. When you reflect, you're still on the unit circle. So that should also be there, but we'll talk about that in the next lecture. And corollary is that can build a measuring device for any u comma v perpendicular on the circle. Okay. And so let's get some, do some examples to know what this projections will be, right? So let's say my u, if I take plus, which is 1 over square root 2, and if I take a minus, which is 1 over square root 2 times this. Now these two are perpendicular, right? You can also see it visually. One is at angle 45 degrees. So this is plus, and the other one is exactly here. Right? This is 90-degree angle. Okay. Now imagine I have the device for it. Nature, in its kindness, allows me to build this device. Okay, which I'll call the H device for Hadamard device. Okay, and suppose I pass in the state 0 to it. What happens? Okay, so I have to calculate what are the outcomes, right? To calculate the outcomes, what do I need to calculate? I need to calculate what are the lengths of the projections. Okay, so this is my 0 vector. I need to project this vector along these two directions, and I have to calculate the lengths. Okay, so you have to become like a high school, you have to recall your high school geometry. You do it in high school here? I didn't do high school in the US, so.
Yeah, we do that.
Okay, so you project, you get something here. You project, you get something here. Okay, and what are these lengths? Any guesses? Yeah. Sine and cosine of these angles, right? So you can always compute the projections by the angles. Okay, so in particular, what you get is going to be plus with probability half and minus with probability half, because the lengths are basically 1 over square root 2 and 1 over square root 2. So squares of the length is half and half, right? So you can think of this measuring device is another way to produce states which are purely in plus or purely in minus. I can do this. If I want something purely in 0, just pass it through this measuring device. It's either going to be in 0 probability half or so on and so forth. Okay. And you can do the same thing. What happens if I pass in 1? Well, you have to change what you're projecting, right? So this is your point, you project, kind of you end up with, the lengths are not going to change really. Okay. Again, you can calculate these by cosines and sines. So you end up with the same outcome. So for this measuring device, 0 and 1 look exactly the same, right? For the horizontal measuring device, plus and minus looked exactly the same. right? You only see 0 with probability half or 1 with probability half earlier. Whereas here you see plus with probability half, minus with probability half. Okay, any questions about this? Let me make sure I started recording. Yeah. Any questions? Also easy, right? Okay, now let's do some counterintuitive stuff. So there is something called a horizontal polarizing filter. It's not the measuring device, but it's an actual filter. It's not the same as a measuring device. And these are not some sophisticated $1 million things. If you have 50 cents, you can order them on Amazon. I mean, you can order them in bulk, these filters in bulk. And anytime you have polarizing glasses, they are really horizontal filters. Okay. So what is an horizontal filter? Well, it's something which, if I pass in a photon in these states, it does two things. First, measures, in the 0 or 1 basis. Okay. If outcome is 0, lets it through. If outcome is 1, then photon converted to heat. It has some absorption thing, which basically, it measures in 0 or 1 basis. If the outcome is 0, it goes through as it is. If the outcome is in 1, it's converted to heat. All right. So if you pass, something which is 0 through this horizontal filter, what happens? It just goes through. Nothing changed, right? Measurement outcome would be the same, so just goes through. And if I pass 1, what happens? It never goes through, right? So if I shoot a laser beam, which is only producing things in this polarization through this horizontal filter, it will be pitch dark. Okay? Nothing. And if I pass something which is like this, which is plus, then kind of 50% of the time, you see light go through, right? And, heat 50% of the time. Okay. And that's the phenomenon, that's the principle behind your polarizing glasses. Basically, when you have your polarizing glasses, photons are coming around in all directions. Their, alphas and betas are basically completely random. So, things get through 50% of the time. Okay, they're roughly like this. Again, everything is random, right? On average, if I shoot, so polarizing glasses, and if you're into photography, you have circular polarizers and whatnot. If I shoot 1 million photons at random, then about 50%. Okay, so light intensity drops by 50%. Okay, and in the special case of polarizers, there is this beautiful quirk that you can get a vertical filter, vertical polarizing filter, by just rotating your thing. Okay, so if you take two glasses, polarizing glasses, two pairs of sunglasses from your favorite dollar store, stack them up, one horizontal, one vertical, you'll see zero light going through. You can actually do this experiment. Okay, I didn't have lens. I mean, I couldn't find glasses today morning. Otherwise, I would have got them here for you to try it out. But you know, that was unfortunate. Otherwise, it would have been fun to see it. You need a little bit of a dark room to see that nothing is getting through. Otherwise, you will actually see this happening. Okay, so here, if I pass it through this, then you'll see one with probability beta squared and heat with probability alpha squared. Okay, so I mean, so what I said just now is that, you know, imagine I do this experiment, right? Use a laser, just shooting things through. Okay, so, you know, this is 100% brightness. What should you expect here? About 50%, right? You know, half of the time, you know, things are all random. So maybe half of the time you go to heat, half of the time you actually let the photon through, right? And if I stack a vertical filter here and I put a light screen, let's say, right? So you have 50% brightness, but all these photons are in one direction now, right? Things were initially random to begin with, but once I pass through this horizontal filter, you know, the brightness has decreased, and not only that, but the states have also changed to only be along zero. Okay, now, but the vertical polarizer, the probability that a photon gets through is exactly beta squared and heat is alpha squared, right? You know, you heard alpha is 1 and beta is 0, nothing will get through. Okay, so you will see 0%. And as I said, I didn't have the two filters at home today, but if you did, you can do this experiment in any room. Okay, I encourage you to try. Now here's an even funnier quirk. Instead of getting horizontal and vertical polarizers, you can also get diagonal polarizers. Has anyone used a circular polarizer in photography? So these are like these filters that you get in front of the lens and you can rotate the angle. And that's exactly what this is. So what do you think if I rotate this, you take your polarizing lens, use your sunglasses, put them at a 45-degree angle. What would it do to a photon? Any guesses? It's like 50%, but basically it does what horizontal was doing for 0, but for plus, right? It's along this plus direction, right? So it moves everything to that direction. Okay, again, you know, that's what nature does. You know, when you rotate it, it only lets light in this particular angle through. Okay, so just as we said, so it measures in plus or minus basis. If the outcome is plus, lets it through, outcome is minus, photon is converted to heat. Okay. So that's a nice thing about quantum mechanics. Everything is kind of, you know, makes sense after you take this postulates. Once you take these 3 laws, they obey the laws of, you know, your plane geometry. If you rotate, okay, the natural thing would have been, okay, things along this would go through, things in the perpendicular direction don't go through. And that's exactly what happens. Okay. Any questions about this? All right. But then let me throw a wrench in your understanding. As I said, if this is not confusing to you, then the first time you see it, then you're not seeing the full picture. Okay, so new experiment. Guess what I'm going to do? Yeah. Yeah, put the one in between. You know, any person, if I ask my kid, you put these two things together like barriers, light is not getting through. If I put something in between, what should happen? It should only become harder for light to get through. Okay, let's see. So imagine now that I put okay. So now what happens? Well, things get through 50% brightness, but everything is in state 0. And here what happens? Yeah. 50% of that, which is 25% brightness, but everything is in plus. Right? So this change of the state changes what happens subsequently. It's not just we're measuring, we're changing the state of the photon. Right? So what comes after that? 50% of that. You know? So you get 12.5%, 12.25, I guess.
Times 2 is 24.5.
Oh yeah. And then everything is in state 1. Okay. So this is very counterintuitive, right? You know, you had two things which are blocking light completely. Why would adding a new barrier? You should think of it as a barrier, right? Because if I put it separately by itself, it decreases the intensity of the light that goes through it. It never increases the intensity. But when I put it in between these two, the net effect is an increase in light intensity. Very pathological, but something that we can just see from these 3 laws. Okay. Any questions about this?
What do you mean when you say pathological?
Counterintuitive, right? You know, I have something which blocks light. This diagonal filter, I know, blocks light. These two things block light completely. I put this other thing which blocks light in between, and suddenly light is actually going through. Yeah.
There's a reason why there's some photons that would possibly survive, because there's parts of flux that are also like could be vertical, like it has some probability to be vertical as well.
Yeah, that is true. But the main thing, I would say the counterintuitive thing comes from the fact that putting this blue filter is changing the state of the photons. If it was just measuring, if it just said, okay, 50% of the time I'm going to let light through, but it's changing what is going through as well, right? Yeah.
Why doesn't it force all light to be in 0 all the time after the first filter?
Because the blue diagonal filter has its own basis, right? It only thinks, you know, it lets light through only 50% of it, basically with probability this much. And when it lets light through, it's only in the plus basis. Plus vector, sorry. If the outcome is a minus, then it's converted to heat. It completely disintegrates. Otherwise, it lets the photon through in this state. Okay. So, you know, it's transforming what is going in and also acting like, I'll discard some things. Okay. Yeah.
If the horizontal filter forces the photon to be zero, then how can it pass through the diagonal?
Sorry, say the question again.
The horizontal filter
Mhm.
forces the photon to be zero, then how can that pass through the diagonal?
Right. So the diagonal filter, what does it do, right? It measures the incoming photon in the plus or minus basis. Okay. And when we measure what is the outcome, it's plus with probability, which is proportional to the length of the projection of 0 along plus, which is half, right? Then it goes through. Or it's minus with probability half, then it gets converted to heat. Does it answer your question? Any other questions? I mean, this is really like, mind expanding as far as the way we see physics. It's not just because of, okay, this class, but, this is the physics that we see all around us, right? Unless you see this careful experiment, you don't see this contradiction or counterintuitive thing. Yeah.
When we say measurement, do we actually get like a probability, or is it
Just the outcome.
just
We
a
never,
computation?
just the outcome. We don't know the numbers alpha square and beta square. It's as if there's, something inside. What comes out is in state 0 or in state 1. Either of these two things happen, but only one of them happens.
But if you ran it infinitely times zero.
But you only get one photon, right? I mean, you can send a different photon, but that's a different photon. You can't copy the photon. There's this thing called no cloning in quantum mechanics, where you can't just duplicate things for free. But there is a many worlds interpretation of quantum mechanics where you reason that, every one of these branches is happening in a different universe. And somehow we are seeing some constructive interference between all of them. But, it's, as I said, we are just going to shut up and calculate. We're not going to ask these questions again and again, but we will investigate the computational implications of these things. Okay. Yeah.
Is the input to the above diagram only can be plus and minus?
It's random, like, just a laser beam, which is generating, you can imagine is generating photons in random states, like alpha 0 plus beta 0, where it's a random point on the circle, a million of them across.
Why is like 50% of it zero?
Because, roughly speaking, if I generate alphas and betas at random, alpha is roughly 1 over square root 2 and beta is roughly 1 over square root 2. That's a good question. If I send them exactly in plus, then it would be 50%. But even if I do a million times at random, I should see things average out to something like this. Okay. And I mean, as I said, this is something you just need, maybe like $5 or something to do this experiment in your home. Okay. All right. So we have all the ingredients to talk about quantum computing now. But what we will do in the next lecture, the plan going ahead, is first extend QM laws 1, 2, 3 to what are called qubits. Okay, again, technically it's not needed. I can only just work with bits, but notationally it makes things clearer. Qubits means basically instead of just having 2 options, you might have D options, like 10 options or 100 options. Typically some power of 2, but we'll talk about that. All right. And then we'll see quantum circuits.
Professor, we lost audio again. Professor, can you hear us? We lost audio.
Okay, somebody make me the host again. Okay. Can hear, make me the host. Where is the host? There we go. Cool. Okay, so in this movie, someone comes and says, okay, I'm build this bomb, which is tied to a polarizing filter, or I just give you an empty box. So either it's EV bomb or the empty box. And your goal is to decide which is which without, actually blowing yourself up. Okay. So if you were to try and do it, without any quantum mechanics, you would send a photon across and either it just goes through. If it's a dirt, it always just goes through and nothing happens. And if you're in the bomb setting, something happens. Okay. So what is one strategy that you can come up with? Simplest strategy.
Don't ever let one through.
Well, but then you don't know which scenario you're in. Right? Your goal is to find out whether it's a dud or a bomb without actually blowing yourself up. Yeah.
Put a vertical filter before the box and then send a photon through and see if any light comes out of the box.
Well, let's try that, right? So let's say you send a photon, but then you put a vertical filter. So essentially you're only sending things in one, right? So in the empty box case, the light goes through, perfect. But in the bomb case, what happens? You're not joining the bomb squad. Right. Boom. So we did find out there was a bomb, but then at great cost. Okay.
No survivors.
Right. So here's the thing though. Think about this. I think it's a fun puzzle to think about, really counterintuitive. But basically, give me any number. And 1,000, I can tell you what case we are in. And with, I'll say time n, meaning basically I'm going to use this box n times essentially. And chance of exploding is 0.001. Okay, I'll tell you what case we are in with 100% certainty. Okay, after this many times, but the chance of exploding is very tiny. Okay, and we'll see how to do this in the next lecture. But I encourage you to think about it because it's very counterintuitive, right? So we are in with very high degree of certainty. Okay, I think there's a question. Is there a question in Zoom? I see a raised hand.
Oh yeah. I just wanted to. Oops, it's
Yeah.
echoing.
Is this generalizable just to like 1/n for chance of exploding? Or-
Yeah, it's basically 1/n. Yeah. Is it 1/n or it might be 1/√n, but yeah. Let's say tiny sense. Yeah. No, it is 1/n, I think. Yeah. Yeah, but then you have to do it more times. Yeah, we just want, we can probe it, send a photon through. That's what you can do, but you don't want it to explode. Okay, so yeah. So you have to probe it very differently. Your algorithm changes. You should think of it as like time somehow, right? The more time you allow me, the more certainty I have. Okay. We'll talk about this, the solution to this puzzle. We'll work through this in the next lecture. Okay, so I'll see you all on Monday and have a fun and nice Thanksgiving.